So let us start with psychrometry. Psychrometry, or it's otherwise called as hygrometry, it's the field of engineering that deals with the determination of physical and thermodynamic properties of gas vapor mixture. So it's the field of engineering that deals with the determination of physical and thermodynamic properties of gas vapor mixtures. And let's start with the terms that are usually dealt with in psychrometry. The first term is dry bulb temperature. So dry bulb temperature or just temperature or air temperature, it all refers to dry bulb temperature. So even if they say just temperature or air temperature, it all means dry bulb temperature. So this is the temperature of air measured in a place that is shielded from direct solar radiation. So temperature of air measured air in a place shielded from direct solar radiation. So no other fancy definitions attached to it. It's as simple as your air temperature. Now let's move on to wet bulb temperature. Your wet bulb temperature basically indicates the cooling effect due to evaporation. Now what does that mean? Let me explain. So how it is usually measured is, this is your temperature and the bulb of it is usually covered with a wet cloth or a wick. So it's covered with wet cloth or wick. Now imagine the hair around it. So the air around it is too dry. So the air is too dry. So what does it do if it's too dry? It takes up the water vapor. It takes up the water vapor from this wet cloth by evaporation and takes it into the air. So what will happen? The temperature here would become lesser. Now imagine the same scenario. Your temperature covered with wet wick, but here the air is too humid. So it's too humid, which means it has enough moisture content here. So too humid, so it has some amount of moisture in it. So what does it do? It takes very little amount of water from the cloth by evaporation. So here the temperature would be comparatively higher. Now imagine, no, before that, whatever the temperature higher or lower I'm talking about would be always lesser than the dry bulb temperature. So your wet bulb temperature would always be less than your dry bulb temperature. So let's consider what does this mean. Imagine the air temperature or your dry bulb temperature to be 30 degrees Celsius in both the accounts. And since the air is too dry, it takes up a lot of water. Then here the temperature that you would find is, let's say, it's 25 degrees Celsius. And since there is already some amount of moisture in the air because it's already humid, it takes very less amount of water from due to evaporation. So the temperature is comparatively higher, which means, let's say here it is 28 degrees Celsius. Any which way, the temperature is less than dry bulb temperature. But if you compare both, this would be higher compared to your dry air. So that is what I am talking about. Now imagine a third case scenario where the air around you, where the air here, it's 100% saturated, which means it does not have any space to take up any more water vapor. In that scenario, your wet bulb temperature would be equal to your dry bulb temperature. Okay, I hope this is clear. Let's move on to the next parameters. Now, your dry bulb temperature minus your wet bulb temperature gives something called as the wet bulb depression. And the bigger the difference, the more dry the air, the smaller the difference, the more humid the air. Now, what does this mean? Let's again go back to the same example. Here, the dry bulb temperature is 30 degrees Celsius. Your wet bulb temperature is 25 degrees Celsius. Your wet bulb depression would be 5 degrees Celsius. And here, it would be 30 degrees minus 28 degrees, 2 degrees Celsius. So, the more dry the air, the bigger the difference. The more humid the air, the lesser the difference. So I hope it's clear. Now let's move on to dew point temperature. So dew point temperature is basically the temperature at which the air or the water vapor condenses into dew. So this is the temperature at which the water vapor turns into dew, and this is the process of condensation. Basically the process by which we get rainfall. So that is your dew point temperature, and your dew point temperature is always less than your wet bulb temperature, which is always less than your dry bulb temperature. Oh, this is dew point temperature. So dew point temperature. Yeah. Okay. Now let's move on to another parameter, which is corrected effective temperature, which is CET. So what does this mean? I'll start with an demonstration of an example. So imagine this is a room and you're standing in it. The general air here is your air temperature, which is your dry bulb temperature. Now imagine the air is humid. So your air temperature plus it's humid, the air is humid, so it's humidity. And when you add these two, you get something called as the effective temperature. What does that mean? Again, let's go back. So imagine the room and you measure the air temperature and it feels 30 degrees Celsius. But then the air is very humid and you add humidity to it. There is 30 degrees Celsius, you add humidity to it. It doesn't feel like 30 degrees Celsius, it feels a bit more than that. So what does it mean? It feels like 32 degrees Celsius. But these are like examples I'm talking about, so keep that in mind. Now imagine you are adding a fan to it, which means you're giving air movement. So all this air is coming over you and you feel okay. So you give the air movement. With the inclusion of air movement, you feel okay and you feel at 30 degrees Celsius, or let's even say you feel at 28 degrees Celsius. Now imagine all the walls around it are hot or like gives off radiation from the heat. So these give you radiation heat from your surroundings. So your radiation heat. And with all that, the temperature that you feel is at 29 degrees Celsius. So what is corrected effective temperature is the temperature that includes your air temperature, your humidity, your speed of air, your radiation heat. So all these parameters combined gives you corrected effective temperature. So what does this mean? This basically means how hot it actually feels to your body in real space. So how hot it actually feels to your body in real space. And the parameter that it considers for this corrective effective temperature is air temperature, humidity, speed of air, and radiation heat or radiation of heat. It's radiation heat. So it's radiation heat. Now again, let's look at this temperature. Here we thought the air, we consider our air temperature to be 30 degrees Celsius. But by taking into all these accounts, you feel at 29 degrees Celsius, which means your corrected effective temperature is 29 degree Celsius. So I hope this is clear. So let's move on to humidity. So humidity is the moisture content in your air, and there are different categories under it. So let's look into each one by one. So imagine there's a box, and this box is filled with air. And what is air made of? Air is made up of your dry air plus water vapor. And this gives you your moist air. So the amount of water vapor present to the amount of volume of air is your absolute humidity. Okay, so absolute humidity is the amount of water vapor in the box to the volume of air in it. That is your absolute humidity. So it can be defined as absolute humidity is equal to mass of water vapor to the volume of air. And absolute humidity is also called as water vapor density. Okay, so now let's talk about the moist air. In this moist air, how much is the water vapor present? Okay, so the moist air consists of your dry air and your water vapor. So what amount of water vapor is present in a moist air? So that gives you your specific humidity. So specific humidity is basically how much water vapor is present in the moist air. And the formula is mass of water vapor by mass of moist air gives you your specific humidity. And if you compare the water vapor to the dry air, then that gives you your humidity ratio. So humidity ratio is, if you compare the water vapor to the amount of dry air. Humidity ratio is equal to okay, so I hope it's clear up to now. Then there is the term relative humidity. So what does this mean? This means the amount of water vapor present in the moist air to the maximum amount of water vapor the air can hold. Okay, so this is, it's a ratio, so it's the ratio of amount of water vapor present in the air to the maximum amount of water vapor the air can hold, and it's expressed in percentage, so it's expressed in so this maximum amount of water vapor is basically your saturation point. So relative humidity is actual vapor pressure to saturation vapor pressure into 100. So let's talk about humidity once more and try to understand it. So absolute humidity, imagine there's a box and it has air in it. So the air is a combination of your dry air and your water vapor, which gives you the moist air. So the amount of water vapor to the volume of air present inside that box gives you the absolute humidity. So absolute humidity is equal to mass of water vapor by volume of air. Now the amount of water vapor present in the moist air gives you specific humidity. So how much water is present in the moist air, which means mass of water vapor by mass of moist air. Humidity ratio is the amount of water vapor present in the dry air. So mass of water vapor by mass of dry air. Then relative humidity is the ratio of amount of water vapor present in the air to the maximum amount it can hold. So actual vapor pressure by saturation vapor pressure into 100. This 100 is because it's expressed in percentage. So I hope humidity is clear now. And if you are getting confused between absolute humidity and specific humidity, thinking like volume of air and mass of moisture is the same, then no, volume is different from mass. Now let's move on to our next terms, which is specific enthalpy and specific volume. So specific enthalpy is the total energy of both the dry air plus water vapor per kilogram of dry air, and specific volume is the volume of both the dry air plus water vapor per kilogram of dry air. And if the air is hot or humid, so if the air is hot or humid, it expands and it releases lot more energy. So both your specific enthalpy and your specific volume, they both increase. If the air is cold or dry, it contracts. Here it expands. Which should require less energy and should take up less space. So both the specific enthalpy and specific volume would decrease. Okay, I hope this is clear. Let's move on to the next topic, which is your psychrometric ratio. So the psychrometric ratio formula is R. R. Right. Now let me explain each term. This is your psychrometric ratio. Hc is the convective heat transfer coefficient. So what is convective? Convective is a type of heat transmission. So it basically, so convention or convection basically is the transfer of heat through liquid forms like gases or water, like that. Then Ky is your convective mass transfer coefficient, and C is your humid heat. So what is humid heat? So humid heat is the specific heat of moist air per unit mass of the dry air. Okay, so psychrometric ratio is the ratio of convective heat transfer to the product of convective mass transfer and humid heat. So I hope this formula is clear. Now let's move on to psychrometric chart. So this is a psychrometric chart. It's and let me explain each parameters in it. So all these that's mentioned here, it's your dry bulb temperature. Okay, and everything that's marked on this line is your wet bulb temperature or your saturation temperature. So these are your wet bulb. Like, I meant all the marks here, okay? So the temperatures that are marked here, and all these, curves, these curves that go like simultaneously, all these curves, are your relative humidity. And every all the points that are marked here is your enthalpy. And the almost vertical lines, these form your specific volume. These are your specific volume. And that's mentioned here on the y-axis is your humidity ratio. So let me explain this again. Let me draw here separately and I'll explain it. So this these two are your axis, okay? And whatever that's mentioned here, it's your dry bulb. I'll just write it as TBT, which is your dry bulb temperature, and it increases as it moves this way and it decreases as it moves this way. So let's just say it's here 20, 30, 40, and so on. You have 60, 70, and so on, like 80 and so on. And whatever that's marked here is your humidity ratio, and it's usually called grains. So it's marked here. So you have like say 0.01 or 0.08, 0.07, and so on. And it's the same, increases, decreases, increases as it moves up, it decreases as it moves down. Then you have this curve. Oh god, it's a very bad curve. Okay, fair enough. This is your curve, and any point that is marked in here, okay, all these points are your wet bulb temperature. These points are your wet bulb temperature, and it's also called as your saturation temperature. Like the curve is called as your saturation temperature. And your wet bulb temperature basically, goes crossways. So it goes like this. Okay, like these these lines are your wet bulb temperature. Now projecting from here are your enthalpy. So these are your enthalpy. And your almost vertical line, not vertical lines, but almost vertical lines like this that goes these ways. They are your specific volume. So again, let me mark them. So these lines, they are your specific volume. Now the dry bulb temperature is not just marked in this region. The line also goes up. So all the vertical lines that you see are your dry bulb temperature. So these are your dry bulb temperature. And the curves that go along these lines, the curves, these curves are your relative humidity. Okay, so let's mark again. These curves are your relative humidity. And the line that goes from the humidity ratio and intersects at the wet bulb temperature curve, the point that it makes. So basically this point, the point that it intersects at, gives you your dew point temperature. Okay, so I hope this is clear. So let's consider it now with an example. So let us consider a temperature of say 70 degrees Fahrenheit. So this is the point, the line that goes here. And the wet bulb temperature is let's say 65 degrees Celsius. So these diagonal lines are your wet bulb temperature. And now the point that it intersects. So the point that this intersects and the curve that is gonna go parallel to the relative humidity gives you your this give with that okay with the dry bulb temperature and the wet bulb temperature, you can find the relative humidity. This is not very visible. Okay, relative humidity. Okay, so you find your relative humidity. Now what do? You take this point, that is your point of intersection of the dry bulb temperature and well bulb temperature, which gives you your relative humidity, and you join it with the humidity ratio, and after that you extend it, which gives you this intersection point. Now this is between 60 and 65, leaning more towards the 60s range. So let's consider this is 62 degree Fahrenheit. Is it Fahrenheit? Yeah, it's Fahrenheit. So this is your dew point temperature. So I hope this is clear, and let's move on to the strategies that can be done using the psychometric chart. So these are the psychrometric chart strategies. So it's all mostly self-explanatory, but let me just talk about it. So the way we plot our dry bulb temperature and find all these related issues that I talked in this map, after plotting it, you can divide it into zone. So whatever that falls within this zone is your comfort zone, and these are your extended comfort zone. So up to these regions we have no issues, it's all good, it's all fine. Once it stretches into these regions, then we need to think about giving a lot of natural ventilation. Okay, then if it reaches these region, a lot of solar passive solar heating is to be required. Like just you can see the temperature here is just 10 degrees Celsius. So you would need a lot of heating to feel comfortable in that environment. So these are based like what kind of strategies that needs to be done. Like here you need a lot of solar heating, passive solar heating needs to be done. These temperature has a lot of the temperature, like see it's like 25 degrees Celsius, it's not too bad, it's fine, it's well and good, but maybe the humidity is more. So maybe the humidity is more or some other thing is happening, so you need to give a lot of natural ventilation. Okay, then let's look into other places as well. On these regions a lot of evaporative cooling needs to be taken place of. Then you have here where a lot of high thermal mass materials, like thick walls, all those sort of passive design strategies has to be used. And again in these region, not just high thermal mass but also night ventilation needs to be taken care of. So these are the ventilation or design strategies that can be done using the psychometric chart. So I hope psychometric chart is clear now, and let's move on to other topics. So we have something called as comfort ventilation, which is basically the ventilation that is comfortable enough for you in an environment. So sometimes a building, let's say this is your building, and this is your direction of wind. It need not The building need not be always 90 degrees perpendicular to the direction of wind. So it need not always be perpendicular to the direction of wind. It can be, but it is not necessary. A convenient angle can be somewhere anywhere between 20 degrees to 30 degrees. So for example, let us say this is your building and your wind direction is this is, which is east to west. And some east to west is not the ideal orientation due to the radiation and a lot of heat gain. So what you can do is you can orient your building at like say 30 degrees. and you can still get good amount of ventilation. Okay, so I hope this is clear. Now let's move on to the next point. For proper ventilation, the ratio of opening area to the total floor area of the room should be 1:6. So this is the ideal ratio that is followed. Now let us look into terms which has formulas like air changes per hour. So what does this mean? This means the number of time the air in your room for say is changed completely in 1 hour. So that's what air changes per hour means. So and you have formulas for this. If we take natural ventilation, then the air changes per hour is equal to 0.65 into wind speed into area of the smallest opening into 3600 divided by volume of the room. Okay, this is for natural ventilation. And if you see for mechanical ventilation, is equal to 60 into Q by V, where Q is your airflow rate. Okay, so these are the two formulas for air changes per hour. Now the rate of air change depends on certain factors. Let's see what all those are. So first is your design of the opening. The location of the opening, the temperature difference between the inside and outside air, the volume of the room, the type of activity that takes place in the room, the activity type, number of occupants within that room, the speed of air and also the quantity of heat, moisture, and order present in the room. And these are very practical uh, things that we know about, so there is no need much of an explanation here. So what are the factors that depends upon the rate of change of air? So it depends upon the design of the opening, location of the opening, the temperature difference between the inside and the outside air, the volume of the room, the activity kind of activity that takes place in the room, the number of occupants, the speed of air, like the speed of air which it moves into the building and out of it, and the quantity of heat, moisture, and order present in the room. Now, the maximum and minimum air changes is that can happen is the max. First, let's see the minimum air changes per hour should be at least 1, and the maximum air changes per hour can be 60, but the desired is basically somewhere 3 to 5 air changes per hour. Okay, so we've talked about air changes, and now let's move on to heat gain or heat loss. I'm just gonna talk about the formula here. So heat gain or heat loss, or it's even called as heat flux. So the formula is Q is the heat gain or heat loss. So Q is equal to specific volumetric heat of air into V into delta T. Now let's see what each of them is. Q is your heat flux. It's your heat flux, and V. Okay, now let's talk about specific first. Specific volumetric heat of air is mostly 1300 joules per cubic meter degree Celsius. Okay, and V is the total volume of fresh air. So this total volume of fresh air can be found by number of air changes into volume of the room or space divided by 3600 gives you your volume of the fresh air. Volume of the fresh air is not the same as volume of the room, so remember that. And delta T is the temperature difference. Okay, so I hope the formula for heat gain or heat loss is clear. Now let's talk about thermal comfort and the parameters that are used there. So the first parameter that I want to talk about is this. This is your bioclimatic chart by Victor Olgier. So Victor Olgier is the one who founded or made bioclimatic chart. Now let's talk about it a bit. So the axes are basically this is your dry bulb temperature and this is your relative humidity as it's mentioned here. And this has a comfortable zone in it. So anything that's falls into here is your comfortable zone. Okay, so your comfortable zone. And anything that falls in the dotted region, they are acceptable, they are comfortable to an extent, like extended comfortable zone, like how we saw in the psychrometric chart. It's the same way here. And the regions here mostly so anything that falls you know above the comfort zone but below this line, there you need to see what kind of treatment needs to be done. So here a lot of wind is needed, so you need wind is needed. Okay, but still you have to provide as much as possible so that anything comes into the comfortable zone. Even if you're if you point your relative humidity and point it along with your tribal temperature and it's somewhere here, you need to put an effort to bring it to the comfortable zone. It's the same way. So now see these lines. Can you see these lines? Let me say what they are. So what these lines mean is, imagine you're plotting and okay, let's consider your relative humidity to be 30% and your temperature is somewhere 35. So where does it gives plots? It plots till this point. And you need to make efforts to bring it within the comfort zone. So you follow this line, and see it's given 1 meter per second. So what does that mean is, if you provide an air movement of 1 meter per second, you can make that temperature with that relative humidity and you can bring it to your comfort zone. Okay, so I hope this is clear. Let's go through it again. So we have a temperature of 30 degrees and we have a temperature of we have a relative humidity of 30% and we have a temperature of 32 degrees Celsius. So it's somewhere we mark the point here and it marks right on this corner. And what you do, you follow this line and you see what it reads here. So it says 0.4 meter per second. So what does that mean? If you provide an air movement of 0.4 per meter second, then you can bring whatever the environment that you have created in your building, which is not in the comfort zone, you can make it come into the comfort zone by providing 0.4 meter per second air movement. Okay, now let us consider another example. Let's consider a relative humidity of 50% and a temperature of say 15 degrees Celsius. So that brings us to somewhere here. So you follow this line and you see somewhere 500 to 300. So let's say this is 400. So what does this mean? If you provide radiation of 400 watts per meter square, then you can bring the environment of your building into the comfort zone. So this is how bioclimatic charts are used. So it is basically used for designing passive uh, design systems, uses relative humidity and variable temperature as its axis, and this is based upon the climate and location of the building, and it's basically used in the early planning stages. Okay, so I hope bioclimatic chart is clear.